Harry Westfahll Jr. is the director of the Brazilian Synchrotron Light Laboratory, LNLS, and an expert in the use of synchrotron radiation for the study of polymers and magnetic materials. And today he will share his experiences building and operating Brazil's fourth-generation light source, Sirius. And I can imagine that there's all kinds of lessons for the community to learn that Harry will present to us. So I'm very much looking forward to this presentation. Thank you very much, Harry, for joining us.
Thank you, Ian, for the introduction. Thank you, John Luigi, and thanks, Tom, for the invitation. It's a great pleasure for me to be here. And I hope to share some of our experiences, the good and the bad, about the construction of our new synchrotron. So let me start. Can you all see my presentation?
That's great.
Okay. Yes, you can. Thank you. Okay, so I'll start by introducing our center. We are in a center for research a National Center for Research in Energy and Materials. This is a non-profit organization working. We have a contract with the Ministry of Science and Technology, and we administrate this campus that started with a synchrotron. So originally, this was only the Brazilian synchrotron light source, and it was the first and the only synchrotron in Latin America. We developed basically all the technologies in the country for building this synchrotron. Started from scratch 33 years ago, and built a community of thousands of users. And in the process, we were able to give birth to Sirius, this new fourth generation machine. Also in the campus, we have the National Lab for Biosciences. This is a leading facility in structural and molecular biology. They do drug development, and nowadays they are intensively working on drugs, repurposing drugs for COVID-19 and for other kinds of medications, especially using the molecules from our biodiversity. Next is the Neuroscience and Nanotechnology Laboratory. It's our most comprehensive lab in nanoscale, nanoscience, nanotechnology in the country. And it has an advanced part of electron microscopy, and they have a cryomicroscopy system that is very complementary to our synchrotron. And the more recent lab of bioscience, biorenewables, they develop microbial platforms for the production of biorenewables for industrial scale, and they study the structure of biomass and in an atomic and molecular scale using synchrotron. So there's a large integration in between these labs and the synchrotron. I think that they being the same campus make the synchrotron look for interesting science projects and help develop the synchrotron and their science as well. So it's a good synergy in between these labs. Speaking of the story of this center, also we had in the early days of the beginning of the Sirius project, actually in 2012, it was when we started getting officially funded for the project. We had this visit from the Canadian Governor General, Dave Johnson, and Peter McKinnon, and Stefan Kittia, and we were all looking at the operation of a small captured beamline remotely from Canada and Argentina in a project science studio that we were collaborating with the Canadian light source. So our collaboration dates from the early days of the synchrotron. Of course, Stefan Kittia was also a member here of our synchrotron and helped us to build the knowledge that brought us to this point. So speaking of the fraction limit, the storage ring, I love Mark's introduction about the subject. I think it was great for introducing some of the concepts and the science that we'll be able. I'll cite some of the interesting scientific aspects that we mostly based our project on. So having a high coherent fraction, and this means for Sirius more than 50% of the beam is coherent, or in the tender X-ray more than 10% is coherent, fully coherent, allows faster coherent diffraction imaging. So it's about a factor of 100 to 1,000 faster than the third generation synchrotrons. And we can reach more easily high resolutions in coherent grading illumination for soft X-ray spectroscopy, for instance. examples of that, of both of these cases are three-dimensional images for biological systems, or looking on the completely opposite side in physics, looking at collective excitations in strongly correlated materials. Also, having a small beam stay clear is where basically how much can you squeeze magnets around the beam. It's one of the important aspects of this diffraction limited storage rings. And this allows you very flexible ways of dealing with the beam. We expect to use some of these concepts that were introduced many years ago on how scanning the electron beam to scan your sample. So we are looking forward to one day to be able to do this with Sirius. We foresee these in the project in the future. But not only that, but also one of the key aspects is with the kind of small beam you have, not only you have more coherence, but also you can focus beam more easily. And so you can have large working distances from your optics, which allows you to put all sorts of strange environments, high fields, gases, and furnaces, to do three-dimensional image with nanometer resolution in operando. So this is kind of what guided us, the big difference of what we can do with a synchrotron in terms of resolution. Three-dimensional, in operando, and all of this is highly facilitated from a fourth generation synchrotron. So these are some of the aspects of the science, and Mark also touched on how do we bring the beam to do what we want in this, to bring this diffraction limit. So he mentioned the aspects that give you the size and the divergence of the electron beam. We know from diffraction optics what is the size and divergence of a photon in an extended source like an undulator. And if we want to combine this electron as a source of radiation, and we want to extract the most of this coherent fraction, which is a fraction of your beam, is never the entire beam, the best way to do is match your emittance with a wavelength, and to match this beta functions parameter of the accelerator with the size of the undulator, which is typically a couple of meters. And depending on the wavelength, so as Mark said, depending on the wavelength, you're always diffraction limited. But the key factor is that for Sirius, we are diffraction limited in standard X-rays, and with CLS2, you will be diffraction limited in hard X-rays. So it's a very exciting opportunity to work in the systems. A few parameters of our synchrotron. So the storage, the Monochromator lattice, as Mark said, was designed back in 2013. Is about when we closed the design for the machine. It was formerly a third generation design, but it was extremely provoked by the machine advisory committee, which was highly important at this point. Bob Hatter was one of the members of our committee. That pushed the accelerator scientists to think about not a third generation machine, but a fourth generation, the future of the machine, because this machine would be used many years from that point. So this was a key point, a landmark in the project that changed the parameters of the project. And so that's how we reached this, the actual parameters of 250 picometer radians, that with the undulator should fall to in the range of 100. And the beta functions, which are extremely small, and with the combination of what I just said, it gives you a very small horizontal size for your beam. This lattice was designed, and one of the key parameters for the design was that we, as a community also, we had this kind of discussion. And one important aspect is that we wanted the synchrotron to have also bending magnet beam lines. So we incorporated in our design, and the discussion you guys had is just the kind of excellent discussion that's good to have at this point of the project. So the machine and our lab came up with this design where we have strong field bending magnets. Let me just use my laser pointer. These are 3.2 Tesla bending magnets that we use for hard X-rays. We have low field dipoles that we use for infrared and ultraviolet. Yes, we are going to have infrared and UV beam lines, and undulators for the tender and X-ray beam lines with super high brilliance. I will now, this is more or less the evolution of the construction of our site. So back to 2012 was when the project was funded. Starting in basically end of October was when we have this flat land to construct our synchrotron. Then the construction evolved. We had a terrible turmoil during this period in the country, but fortunately we were able to reach at 2018 the point where the building was almost completely constructed. And then we started with the installing the magnets inside the storage ring. So let me see if the movie is going. Oh, okay, now it's going. So what you see now is the assembly progress inside. This is from 2018 when the building was finished, all the way to 2019. So an important aspect also that I should mention is the magnets in the storage ring. We have the booster and the main storage ring in the same tunnel. That saves us a lot of money on the construction. The magnets of the storage ring, they were all built by a Brazilian company that was famous for building motors and generators, but fortunately they matched with our team to design and build magnets for the storage ring, except for the high field, the super bands. But that helped a lot because their manufacturing capabilities was impressive, and with this matching of competences, we were able to build Sirius, the storage ring. And this is the current stage inside storage ring. So we have the LINAC. Typically, we don't see the light. This is just an animation. This is the LINAC. And now I'll walk you inside the storage ring. We are in the commissioning phase of the storage ring and of the beam lines at the same time. I think this is not so usual. But as you go through this movie, you see the internal part is the booster. It brings the energy all the way to 3 gigaelectron volts. And the main storage ring, you see all those magnets and the band micromagnet. And from this design, then we have the beam coming through this the vacuum aspects of the vacuum pipe. The tubes are we use NAGS technology that we also learned from CERN. So all the key aspects of technologies for synchrotron, they were learned during this project, and they were applied, and they were transferred to Brazilian industry as well. So what you see now is the front end that we have companies here in Brazil building for us, and not only the accelerator. So outside this front end now is where we start the beam lines. So now I'll give you a tour to all our beam lines, and I'll start speaking about the science program that these beam lines will have. So we basically are funded for 14 beam lines. The first funding came for 6 beam lines. So these are the 6 beam lines that we are currently building. In the end of last year, we got the funding for the other 8 beam lines, which I will describe quickly. But the first 6 beam lines, they are basically protein crystallography beam lines. This beam line called Monochromator. All the names are names of trees. They are named, the beam lines are named after trees or animals from Brazil. And just take my laser pointer. So Monochromator is a protein crystallography. It's the first one to be built and it started operating in scientific commissioning now. CATDT is a coherent diffraction imaging and XPCS beam line, is also in commissioning. EMA is a string commission beam line. It works in from 3 to 35 kiloelectron volts. I'll show some of this beam line. We'll start commissioning in a couple of weeks. Carnaúba is our nanoprobe spectrocytography beam line. It's a tender X-ray nanofocus beam line. It's also in the process of finishing construction, and we should next month start commissioning. Mogno is a zoom-in tomography, and with high energy. It's based on a bending magnet in the super band, so it can use 3 different energies. And IP is a soft X-ray beam line for ambient pressure Higgs and ambient pressure XPS. So the second phase, which we call phase 1B of our beam lines, we have the infrared beam line, which is being constructed already. Cedro beam line is a circular dichroism beam line in the UV range. Then we have a micro-ARPAS beam line, powder diffraction, exhaust beam line, XMCD, also soft X-ray, XMCD and PIN beam line, small angle scattering beam line, and a high energy scattering for pair distribution function analysis. This is also based on a super band, these three beamlines here are based in low field bending magnets. So as I said, all those beamlines will be using modulators, super bands, and low field bands. This completes the 14 beamlines. We are organized nowadays in 6 divisions within LNLS, and we have 3 divisions that deal with these beamlines. The accelerator division, data acquisition and processing, which is responsible for detectors and computing science, and the beamline engineering, which is also the LLS for the construction, design, and maintenance of the beamlines. The engineering part of the accelerator is connected directly to the general director, Jose Roque, of our center, which is also the director of the CDIS project. I will talk about these first 6 beamlines, which are divided into these three different science divisions. And so I will start with the MACA beamline, which is a protein crystallography. This beamline works in the range of 5 to 20 kiloelectron volts. And the idea is to do serial, micro, and nano protein crystallography. It has 2 experimental stations. We are currently building the first one. It was the first, and one of the features that we also heard from our communities, the possibility of using microbeams, so a couple of microns, all the way to 100 micron beams for different crystals. So having this flexibility and stability in your beam is not so trivial. But having a 4th generation synchrotron and a small beam makes life much easier for the optics as well. So with just a couple of mirrors with a very large working distance, you can still play with different arrangements to have this variable beam size. Now I'll show you a movie that is just the current state of the protein crystallography beamline. So as I walk you, unfortunately you cannot come with me, but I made this video recently so that we can walk together inside this beamline. And what you can see now is the experimental hutch. It was just one step in between measurements. So you see the crystals and the protein, they were just about to take another measurement. And with this beamline, we were kind of finishing the construction and starting the commissioning. We were just in the beginning of the pandemics, and it was sort of interesting to have this. This is just a small video showing how commissioning can be done remotely. We only had a couple of people in the hutch working here because of social distancing, but we were still able to do commissioning and start the first measurements. And this was all basically to start with the first measurement with a crystal from the COVID virus. And also we have now running programs and plant-based polysaccharides on the biorenewable lab. Second beamline I'll show you is the coherent scattering beamline. So this beamline is also under commissioning. So it's a standard X-ray beamline that goes from 3 to 24 keV. And the idea here is to bring the beam from the undulator with a very slight focusing, such that the beam is almost collimated in the source. So it has a very large depth of focus, a couple of meters. So you reach the sample with a 50 micron beam that is almost perfectly collimated. And in this tunnel we have a detector that we developed of almost 10 megapixel. I'll show you some details of the detector. And the idea is here to be able to do coherent diffraction imaging and to do XPCF, the kind of exciting experiments that we'll hear from Professor Sutton in the next talk. This is just a walk through the beamline. As I said, the beamline is currently in commissioning. We have some exciting results. Unfortunately, I won't be able to show them right away. I will have to wait for the news. But as far as you can tell, the commissioning is going very well. What you see now is inside the experimental hutch, so the scattering tube, as it leads to this large tunnel. It's a 30-meter scattering tunnel. Inside we have the detector that we developed. I'll say some words about the detector. And again, it's a beamline that is in the process of commissioning. As I said in the beginning, one of the key aspects is to have in our scientific program, to have the possibility to use different environments for samples, like extremely cooling, cryogenic cooling for avoid being damaged on more sensitive samples. but as well to use sample environments with gases, with high temperatures to study catalysts. That's one of the strong scientific programs in the country. So this beamline was prepared to have this kind of name sheets, very similar to the ones, actually they are borrowed from the ones that we use for electron microscopes, and systems for monitoring the temperature in the sample, not the temperature on the ship. So this beamline is basically in the process of commissioning, and I think that one funny aspect of all this story is that as we commission the storage ring also, we are basically splitting time in between commissioning the storage ring because it's not finished yet. We are working currently with a current of 40 milliamps. We may be able to reach about 100 milliamps soon. But right now, the beamlines are being in a process of commissioning, so this current is not really impacting the scientific programs. In fact, for protein crystallography, the one I showed you before, the coherence of the beam and the ability to focus with just a gentle and curvature of mirrors, it's so large that we have a high flux anyway, even with 40 milliamps in the machine. So next, I'll show you the nanoprobe beamline. This is one of the beamlines also in construction. This is a beamline for doing scanning probe microscopy. It works in the tender X-ray, so it's not a conventional 6M, but it's a scanning probe as well. But we work with 2 to 15 kilo electron volts. One of the key ideas was to have a beamline with nanofocus, but that would be completely achromatic, so that you can change the energy and you do scanning of the energy in the nanospot. So for that, we have this kind of 4-crystal monochromator that we developed here also. We do focusing in 2 steps so that we can maintain a large sample to detector distance and sample to optics distance, again, to allow different sample environments and to allow us to bring environments that normally would be difficult to do in a 3-dimensional coherent diffraction imaging. This beamline has 2 experimental stations. One experimental station is basically to work with a submicron, let's say, beam that goes from half a micron all the way to 100 nanometers. We have a nanoprobe. This focusing property of our submicro station in the beamline, it's basically to have a large working distance, and this gives us this small aperture that leads to a diffraction limit focusing. So it's basically the diffraction limit. It's not limited by the storage ring, but by the aperture of the mirrors and the distance that we want to keep to put the environments. Now the second experimental station, it's already focusing in a few nanometers of imaging, coherent diffraction imaging, and so it has a larger aperture, and it only works then with cryogenic samples. So it's a cryogenic sample-based nanoprobe. From here you can see the installation of the first mirror that this is currently under baking, and you can see inside of this mirror, these gold plates and braids are basically for cooling, extracting heat, because you don't want to deform the mirrors as you focus. And going outside, we have lots of these beam monitor systems. I cannot stress enough as an advice for anyone building a new machine, new beam lines, how important it is to put so many, as many as you can, monitor devices in your system. This is just engineers preparing the second mirror to go inside the secondary focusing hutch. So as we walk here, we just went from one hutch to the next hutch. Now we walk to all the way to the end of this beamline. This is a very long beamline. This is the longest we have. It's 150 meters beamline. So why is this so long? Again, because we want to keep focusing properties and the magnification such that we can still work with large working distances. And I'll show you just an example quickly of some pictures of the experimental station being built. This is the monochromator. It's based on 4 crystals, so crystal bounce. In here, we will have the experimental stations. First one is submicron. The second one is nanoprobe. This is the control room for the beamline. And this is the kind of environment that we expect to have around the beamline. So this is a multi-purpose technique. We'll have the X-ray beam coming through, microscopes to observe the sample, but X-ray fluorescence, X-ray excited luminescence, psychography in forward direction, diffraction. So it's a multi-technique beamline with a staying probe. The sample stage, as I said, is going to be just this tiny little pin over here, but it's going to be in an environment that it can run gases and it can run at high temperatures. And the idea here is also to work, as I said, three-dimensional imaging with inoperando in situ conditions. So this is a more flexible experimental station. Building a stable nanometer nanoprobe with this kind of tubes and gases running around is not an easy task. So we spend a lot of time in the project of this experimental station. And what you see here is already this Tarumã, this submicron to 100 nanometer experimental station. And in construction, in a couple of weeks we should bring it to the beamline. Just an example of how the sample is inserted with the microscopes and the position for the detectors. On the right, what you see is the nanoprobe, which is a very ambitious project. We are building these stations to be stable within the 1 nanometer range. As far as we can measure right now, this is done in partnership with a mechatronic company that helped us also to build the monochromators. But as far as we can tell right now, we are reaching close to this limit of stability. Running scanning image with three-dimensional capability at 1 nanometer stability is a daunting task, but it's some of the key aspect technologies that you have to build up for a machine to use the entire power of a fourth-generation machine. Going up to the microtomography beamline. So this one is the first I'm showing you that is based on a superband. So it uses this, the critical energy of the superband is 20 kV, so it's very nice to have this in the machine. So we can have as much as 20 beamlines, basically this is a 20-fold symmetry. So we can have as much as 20 high energy beamlines because the antennae magnets are already incorporated. And this beamline uses the focusing system very near to the source. And creates a conical shaped beam where you can put your sample and do tomography in a cone beam geometry, so-called. This allows you to use low resolution image, define regions of interest, and do interior tomography with a much higher resolution image. Also use different environments. Again, I cannot overstress the importance of doing in situ and operando condition imaging. That, I think, is one of the key aspects that makes the synchrotron much more powerful than any other technique. And so the general idea of this concept of this beamline is to have then this conical beam. As you want to look at large and thick sample, right? You can look at samples as large as 40 millimeters with tens of micrometer resolution, define a region of interest, and bring it to near the nanofocus. And then use the maximum resolution of the beamline, which is 100 nanometers in this resolution. This is an overview of what's going on in the beamline. We assembled this part of the experimental station in the beamline with the white beam before the mirrors come, so that we could show the first image in the end of last year. When we had the first beam in the machine, 1 week later we were able to show these images, which was good, important for the project. That was the main purpose of this beamline. Advancing this part of construction of the beamline was to show that not only we could have an actual beam, but also we had the entire pipeline of the beamline. Now, by the end of the year, we stopped this operation with white beam, and we start installation of the mirrors to create this conical beam that will propagate inside this big 30 meters tunnel here. It's in air because this is a high energy beamline. But the idea is that we have the beam propagating and we have this rail where the sample can walk through inside this big tunnel and to do this zoom in tomography. I'm about to finish, but this is the stream conditions beamline. So again, having focusing ability with large working distances for this beamline is important as well, because we want to probe samples, probe matter under very extreme conditions. In this beamline, we can probe matter under very small temperatures, very high, nearly Kelvin, thousands of Kelvin, 11 Tesla of magnetic fields, and hundreds, up to almost 1 terapascal of pressure using diamond Mendel cells, which is a program that has been developed over the last year in the previous synchrotron, and it was also transferred to this. It was one of the inspiring scientific programs for this beamline. But the idea is basically to probe wide range of parameters in the phase diagram of different materials. This is a beamline that is about to be commissioned. You see here is a baking of the first components, monochromator. The quarter wave plate that allows us to do dichroism, so it produces circular polarized radiation. And inside the experimental hutch of this beamline, the first element you see is the first experimental station with the KB and the experimental station. Here in the middle, this is a pretty large hutch, but here in the middle is where we install this big magnet and the diffractometer. And this is just the control room of the beamline where we expect to operate these experiments. Last but not least is of the first phase, the 6 beamlines that I showed you, is the soft X-ray beamline. You will have 2 experimental stations, one for near ambient pressure SPS and the other one for RICS. So you see the RICS spectrometer. Another great advantage of 4th generation is that we can have smaller spectrometers with the same tens of milli-electron volt resolution that we would expect only in 3rd generation to have with much larger spectrometers. So the beamline is also based on mirrors and a plane grading monochromator. And what you see now walking through, the hutch is finished. We are assembling the spectrometer, the monochromator, and the mirrors. All the systems, except for this monochromator, all the systems were all built here. They were finalizing the construction. And we will now start putting these elements inside the hutches. What you can see here is also this beamline has the spectrometer and the SPS. They stay in this area, one of these areas that goes outside from the building. What you see now is just the granite, this circular granite, where we slide the spectrometer to vary the scattering angle as much as the inelastic energy exchange. So, just to give you an idea of what we went through, this is the development of our monochromator, and it was very important for us to start with this project for R&D in the beamlines in terms of beamline technologies. Back in 2015, we were basically drawings with my partners, these partners that we work with us in mechatronics. And we evolved the project to the point that now we are still testing commissioning in the beamline, but the offline test showed that we can do a nanoradian stability even at fast scans at 1 kiloelectron volt per second scans. So this is one of the, we had several developments that I showed you, but this one I can tell you that was probably a stepping stone, and it built the capability of our team. We use this to basically train the team of engineers into new mechatronics technologies. As well, we entered the Medifix Collaboration Consortium also 8 years ago. And from there, we developed our own area detectors based on this Medifix chip. It's a hybrid pixel detector. And we partnered with this company here in Brazil to build detectors with up to 10 megapixels with 1,000 frames per second. What you see here is a picture of the largest detector that we have inside the tunnel of the Coherent scattering beamline. And what you see is just a demonstration of this 10 megapixels transmission imaging of a disk running at 720 RPMs. So you can see by the high frame rate of this detector, you can see the beam, you can see the disk turning around. To finish, one also thing to ponder for these new facilities is how fast the experience will be. These experiments typically, if we are lucky enough, they will run, the data acquisition times will be in the range of minutes, as different from, much different from what we typically do in third generation. So a lot of your time will be spent doing sample synthesis, preparation, characterization, pre-characterization, and modeling. So what we decide to do in our synchrotron is to extend what a typical user do in a facility, some simple sample preparation and data acquisition, and extend to allow a faster feedback into sample characterization and modeling, basically providing labs and computing infrastructure. So what I'll show you then is some of this infrastructure. This is one of the labs that is open for users. It's a chemistry lab. So we have all some synthesis capabilities for the users inside the lab, so they can bring their sample, their samples and prepare it here. And thin film growth lab. This was part of our previous synchrotron, but we now have a dedicated station where the users can prepare their samples for ARPs and for other techniques as well. So I talked about the labs, but the important also is the pipeline strategy for data that you adopt and how do you bring to the users this capability. So designing the detector was important because also we could design how the data was going to flow through from the detectors to high performance computing. So we tightly integrated GPUs in the detectors and the storage system. So the entire design of the data acquisition system was worked out from our team, which includes, of course, we started now with 2 petabytes of storage for these fast detectors. You cannot underestimate the amount of storage space you will need for that. This is our data center. And in the amount of clusters that you have to provide. So in our view, this was necessary to extend the data acquisition pipeline. But also we have to develop the tools that the users will use. So these are just 2 examples. We have partnered with NVIDIA as well. We are using some of the new tools for 3-dimensional analysis. This is just an example of 3D CDI. It's not a real data. It's just an example of what we expect to use for data analysis for doing 3D CDI. And in the right, what you see is one renderization. We are investing a lot. We have a specific group dedicated to renderization of this kind of imaging. So to finish, just to say that this was done with a lot of interaction of Brazilian industries. Most of our expenditure was done here in Brazil. And I think that was a very important part of the project that granted us funding and continuation of the project, and also the ability to build what we wanted to build. A question that typically everybody asks is how many employees did you have in the project? So I just put here to consider that this is the most important investment that you have to be done for any facility. We basically, from the beginning of the project, we started with 130 people, and now we are about 310. Obviously, in the beamlines, this is ramping up. We are increasing more than accelerator, which is kind of already leveling off. But it's probably where the major investment that has to be made to start a new machine. So I hope that this is give you some food for thought, and I welcome any questions. Thank you very much.
Thank you very much, Harry. We have several questions of a technical nature, but before we get into those, there's more of a general question, and that is, what was the procedure that was used to decide on the initial beamline complement? And what was the involvement of 1, academics, 2, existing synchrotron staff and users, 3, government, and 4, industry? I wonder if you could give us an overview of the role that those different stakeholders played in designing and the initial complement of beamlines.
Okay. Excellent question, because it's a completely non-linear self-feedback, very complicated and entangled process. Initially, what we did was we had several workshops with the community, and This was back before even 2012. And we got suggestions for what kind of science we could do. But largely, we based our first choices in extending the current user program. So as you see, the initial set was based on doing better for crystallography, doing better extreme conditions. These were scientific programs that were running or doing better small scattering, so then we went back to the community with workshops and user meetings, and we presented, we got our feedback, and we went back to the funders. The industry was not involved too much in this decision-making of the beamlines, but they were, in fact, they were basically trained, had a first contact with synchronous radiation through this project. So, as I said, it was an iterative process for providing some ideas, getting feedback, changing the ideas, and coming to the point that we are now. It's not a linear process.
Thanks very much, Harry. So a few technical questions here. There's one about the insertion devices. What kind of insertion devices can be placed in this ring? Particularly, can you place superconducting wigglers in this ring?
No, we cannot. That's a very good question. Just stop sharing my screen so I can go back to see you all. Okay, stop sharing. So before we had the ultimate design that we have based on superbands, we were thinking about using high energy beamlines, using wigglers like the superconducting wiggler that we used in our previous machine, and I believe c.l.s. also used one of the superconducting wigglers. However, when at some point in the project, when there was a proposal that we could reduce substantially the admittance if we inserted the superbands in the machine. So one advantage was that we could reduce substantially the admittance, but the amount of power that would be consumed by the superbands would not allow us to go into superconducting wiggler. However, the brilliance of the superbands were equivalent to the wiggler because the source point inside the superband was so small that it didn't need so much demagnification in the beamlines. So it was a trade-off. We decided to cover all the high energy programs with the superbands, 3.2 Tesla, instead of using wigglers. And as far as I understand now, and the community also, it was a good choice. But right now, we cannot use any kind of wiggler in this machine. All the high energy comes from superbands. That was the question, right?
Yes, I think you've answered that question very well. There's a lot more technical questions, Harry, and so I'm going to make sure that we get these to you and give you a chance to answer some of these, and we'll post them. I think we have time for one more. And the question is, how do you get a big beam from this ring? So a large beam is desired in some imaging beamlines and lithography beamlines. And the user is just asking, can you actually get a large beam out of a highly coherent sourced ring?
Yes. This is the case of let me share again, maybe. This was exactly the case for these high energy tomography beamline. Perhaps I jumped too fast into that, but if I come back here, okay, there we go. Can you see it? So the idea here is that from this kind of machine, you demagnify the source, so you focus a lot, and this expands the beam, right? So as you can see here, the beam at this distance for this high energy tomography is 85 millimeters. If we allow a longer propagation of this cone beam, so this is if I'm not mistaken, this is a 3 milliradian aperture. So you can do better, even a higher aperture than that. But basically, you focus. Our choice is to focus and let the cone propagate over large distances. That's how we get large beams in our storage ring.
Terrific. Thank you very much, Harry. I think we'll stop the questions here, even though there are quite a few that we have still left unanswered. And as I mentioned, we'll make sure we get those questions to you, and if at all possible, perhaps you could provide a written answer to some of those, and then we'll be able to post those questions. So thanks again very much. Thanks very much for your talk. It was terrific.